Hello everybody, welcome to the last video we're going to be doing for kinematics. This is topic 7. This is kind of the culmination of a whole bunch of different skills getting put together. And this is going to be one of the more challenging topics. I mean, really, that's kind of how every unit works, is that they build and they layer, they scaffold on each other. And what we're going to be doing here is we're going to be talking about the motion of projectiles. And so we're going to have to combine some of the skills we learned in vectors. We're going to have to combine our kinematics equations, and we're going to put this all together in terms of solving a fairly complex problem. And of course, the problems, they can all look slightly different than each other. No two problems really look the exact same. And again, that's the whole point of what makes physics such a challenging but also a cool discipline, is that it really works on your problem-solving skills. And so today I've got about 5 examples, and that's kind of the main point of why we're doing this asynchronously. These examples could take a little while for you to get. They may take a while. And so that's why I want to do this in a way in which you can kind of go at your own pace. And so without further ado, let's get started, because there's a lot to cover today. We're going to talk about projectile motion. And just a quick reminder, a projectile is an object in which the only thing acting on it is gravity. Gravity is the only force acting upon it, which means that it's still going to be in motion, but gravity is going to, if it was on its way up, it's going to get pulled back down. And if it was in motion, it's going to get pulled down. And if it was thrown down, it's going to get pulled down even faster. And so there's really a couple of main ways you can do these questions. One is like I just did, where you throw it up and back down again. Another one's where it's like horizontal and it hits the ground. Another one's where it just goes straight down. You could actually have something go slightly up and then fall down. And really, all of these things, they all have the same shape in mind. And for those of you who have taken or are taking the right topics in Math 20-1 or 20-2, this is known as a parabola. It's known as a parabolic motion, and it involves the same sort of pattern here. So, now, like I said before in a previous topic, we can actually break things up into X, Y, and Z directions. You can actually have things that go kind of not just along the X and Y axis, but also kind of swiveled out along the swivel axis, the Z axis. But just so you're aware, we really only cover just the X and Y directions in this course. We will never do a Z direction. We'll do up and down and side to side, but never in and out. The other thing I have written on the slide is that it's often really important to keep track of all of the variables. A good organizational scheme is important. And so you can see that I'm writing something like this, d subscript y. And that would imply that that's the distance something's going to travel in the y dimension, because we might also have a distance traveled in the x dimension, or a velocity initial in the x direction, a velocity final in the x direction. So I often use different subscripts. The final thing written on here is that whenever we work with time, time doesn't have a subscript. It's independent, because time really happens in x and y at the exact same amount of time. There is no vector amount to time. So what ends up happening then that I've got on this slide right here is that in the x, and if we ever do, but we don't ever do the z direction, so let's just ignore that. In the x direction, velocity should always remain constant. And the reason why is that there's no acceleration in the x direction. If we were to talk about uniform motion versus non-uniform motion, in the x direction we should have uniform motion. But in the y dimension we have non-uniform motion, because we have an extra thing in the y direction, we have gravity. And so because of that, we kind of have a few different pieces of information that you can have. And these are usually the key ones you have. You can usually have a velocity initial in x and a velocity initial in y. A distance you travel in x, a distance you travel in y. But then acceleration only applies in the y direction. Time doesn't even apply for a direction. And if we're breaking this up into a vector, you have an angle. The angle really is what gets you the x and y. You know, we did a few lessons ago where you got to break things up using, say, cosine and sine to try to calculate the opposite and adjacent sides of a triangle. So why don't we get into some examples here? That's really the best way of learning this. Oh, no, I have a couple more slides here before I get into that. I have a couple more pictures. This is a picture of Wile E. Coyote. You've probably seen him in the old Roadrunner cartoons, right? And the classic example that they do is he kind of runs a little bit, right? And then he goes off the cliff, and then he stares at the screen, and he holds up a sign that says, you know, like, yikes. All right, you've seen this before, hopefully. If not, you got to go watch Roadrunner. It's a classic cartoon. Anyways, right? And then he looks down, and then he falls down. But that's not really how gravity works, right? It's not like gravity doesn't take effect. It takes effect immediately. Here's a picture that I think illustrates that concept quite well. what you've got is this dartboard that's on the ground here, right? And what's supposed to happen is the object is supposed to be in motion in the x direction, right? And so it would keep going in the x direction, but it's going to slowly increase its speed in the y direction more and more, right? And so rather than hitting the ground right below the table, right, it has this sort of parabolic shape to it, right? And that's a half a parabola this thing is starting to undergo, right? So hopefully you can kind of see how the Wile E. Coyote example, really this is how it actually is going to work. And so let's get to another picture here that kind of shows this, right? In the x direction is always consistent, but in the y direction is constantly changing due to the fact that gravity is going to make it go up and back down. So here we go. Here's our first example. And sometimes you'll notice that these examples, when we write down the information that we have, I'm going to want to be very specific here. It says a hunting rifle can shoot a bullet at a speed of 350 feet per second. And just to make that a little bit simpler, I'm going to do a quick conversion, 350 feet per second. I need to convert that. And I looked this up earlier today. There are 0.3048 meters in 1 foot. And you may have discovered on some of the assignment questions that I often ask you to do some conversions here. So 350 times by 0.3048 gives us 106.68 meters per second. I just wanted a quick conversion before you start. So I'll usually give you a conversion ratio like this. It says that if the bullet shot along a flat trajectory, that kind of implies that it's basically this scenario here, back here, where we're supposed to be flat, but it's eventually going to fall, right? And so if I could draw a quick picture, this hunter right here is expecting to shoot straight, right? But let's say he misses his target. Well, that bullet's going to keep going, and slowly but surely gravity will pull it down until it hits the ground, right? So let's write out some things that we know here. We were given a velocity in the x direction of 106.68 meters per second. That's how fast the gun can shoot. And you'll notice I didn't put an initial or a final because it's always traveling that speed. Now, other things I know. I also know that my distance in the y direction is 1.3 meters, because as you read that blurb above, it says that he was shooting it from 1.3 meters above the ground. Well, that's it. I only gave you 2 pieces of information. But that's not true. There's always hidden info. Like, for example, the acceleration due to gravity is 9.81 meters per second squared. Or time. Well, actually, we don't know time. Time is something we don't know. But I do know this one, velocity initial in the y direction. Velocity initial in the y direction is 0 because even though he was shooting, I mean, it's effectively, if you were to shoot the gun and drop an object, they would actually land at the same time. So, really, there's no initial velocity in the y direction. It's effectively being dropped. So we actually do have some information here. If I were to take these variables right here, which were all y direction variables, time being x or y, you could write time as being an x or a y variable, then I do have enough information to solve. I can now use one of my kinematics formulas. D equals VIT plus 1/2 AT squared. But with velocity initial in the y direction, I'm just going to put a little note here, this is just for the y direction, with velocity initial in the y direction being 0, I can kind of remove that and make the formula D equals 1/2 AT squared. Rearranging this for time gets you this. It gives you 2 times D divided by A all square rooted. And I can actually solve for how much time it will take for the bullet to hit the ground. And now I know it's traveling really fast in the x direction, but if you were to just drop it, this is how long it would take. So 2 times, and I'll throw in my numbers here, 2 times 1.3 divided by 9.81 square rooted gives me a time value. And as hopefully you've started to learn how to do here, this value here, since I'm probably going to be using it again in the future, as 0.51 seconds, I'm going to store that as letter A. So I will store this as letter A, 0.5148 seconds. It's how long it takes something to hit the ground. And really, whether I was shooting the gun or whether I was dropping an object, that's how long it should take something in the y direction to hit the ground. This right here that I just solved for, this would be using non-uniform motion. That's the principles of non-uniform motion I just used. However, in the x direction, we can use uniform motion principles. Because is there anything speeding up or slowing down the bullet? Well, okay, technically the bullet got sped up. But once it's in motion, the only thing that would slow it down is air resistance, and we get to ignore air resistance in this course. So really, in the x direction, we can just use the formula v equals d over t. And if we want to calculate the distance in the x direction it traveled, that means we'd use the formula v times t. Now you're maybe thinking, well, hang on, Chris, what velocity do we use? Well, hang on, the velocity in the x direction from up here was always traveling 106.68. We always were traveling the same speed in the x direction, and I now know my time value is 0.51. Right. So if I take that a value that I solved for, 0.51, and I times it by 106.68, I can now calculate with sig digs. And since I'm done, I'm just going to round it to the final answer. I'm going to give it 55. I actually got 54.9, but 55 meters. I know how far this thing traveled, 55 meters before it hit the ground, according to this particular scenario here. I just want to check one more time. Yeah, which makes sense, right? 100 meters per second, basically, is how fast it's traveling, 100 meters per second. And in half a second, it would have gone half of 100 meters. So that hopefully makes a little bit of sense. So we were asked to find the amount of time and the distance traveled before the bullet hits the ground, which we now have. It is 0.51 seconds, and we traveled 55 meters. And we only get 2 sig digs, it looks like. So as always, if that made sense to you, that's fantastic. If not, this is where ask me for help, right? I'm in the classroom. Ask me to help out on this one. Let's try another one. So this one right here is actually kind of a cool local cultural example. If you didn't know this, Head Smashed in Buffalo Jump is a location where the Blackfoot people used to chase the bison over the cliffs, these 20-meter tall cliffs. And the bison, kind of like the old Wile E. Coyote, right, kind of thing. Here's the cliff. The bison, just like Wile E. Coyote, they don't just like hover in the air. They eventually, start to fall, and they're going to land and crash. And that's how they killed them, is by herding them over this cliff. And so here's what I'm going to tell you. I'm going to tell you the speed, the velocity initial they were traveling at. I'm also going to tell you the distance in the air they were. And we're going to try to calculate the distance that they landed away from the cliff. And I got to be honest, this is the exact same scenario we just did. I'm not even adding anything new in this one. So here's what I want to challenge you with. Since I already showed you how to do a question like this, where I'm going to give you a speed and a distance, why don't we pause my video and try to solve this before I do. All right, press pause, try to solve it so that you can figure it out before I do, and then come back to it. So if you haven't done that yet, hopefully you are, but now I'm not going to actually wait for 5 minutes in the video. I'm going to go right into this. So here's how you would solve it. Hopefully you've done this. Your velocity in the x direction is now going to be a constant 18 meters per second. In the x direction, you also know time, and we're looking for the distance in the x direction. Those are your x direction variables. In the y dimension, you know velocity initial in y is nothing, because even though they were running, they didn't jump up or down, they just ran flat off the cliff. So there is no velocity initial in y. The distance in y is going to be the 20-meter cliff. The acceleration in y will be 9.81 meters per second squared. And we're looking for time. And once you figure out how this sort of scenario, this particular puzzle works, we're going to solve for time in the y dimension, which means we'll have it in the x dimension, which means we can solve for the distance from the cliff. We can do this. So here's how I'm going to solve this guy right here. First, I'm going to rearrange this formula. It was d equals VIT plus 1/2 AT squared. But again, since VI didn't even matter, when we did this last time around, when we solved for time, time was rearranged to give you 2D over A. That's time. However, in the x dimension, the formula was V equals D over T. So rearranging that, your distance was equal to your velocity times your time. So if I blur all of this together, the distance in the x direction should be the velocity in the x direction. The velocity in the x direction multiplied by the time value, which is square root 2d over a. And I'll point out that these guys were actually y values. So there we go. I can do this all in one fell swoop if I know how to do it. So here we go. The velocity in the x direction was, what did we say it was? It was 18 meters per second. Then we're going to square 2 times the 20-meter cliffs, divide by 9.81. And this will tell us how much distance away from the cliffs this landed. 2 times the square root of 2 times 20 divided by 9.81. All in one fell swoop, I got this number here. And with sig digs, I think it's 36. I'm just going to check my sig digs. Oh, I get 3 sig digs. Scroll back down here. 36.3 meters. And there. So hopefully you were able to do that before I did. If you didn't, hopefully my explanation makes sense. It's the exact same question as the one beforehand. We've now solved for how far away from the cliffs these buffalo landed, these bison landed when they were herded off. So again, if you have questions, let me know. But I've got a lot of examples, so I'm just going to keep going through them so that if you want to pause, you can. If not, here's the next example. An NFL punter is able to kick a ball at a speed of 17 meters per second at an angle of 60 degrees above the horizon. There's a bit of a change to this example, because what's happening here, if I were to kind of draw like a bit of a grid, that the guy is kicking the ball, and it's got like an initial vector of 60 degrees that he's kicking it at. And then the ball is going to go up, and it's going to follow its parabolic path, and then eventually it's going to hit the ground. And so we have different information this time. If I were to write this out, we would know that the velocity initial is 17 meters per second. Yeah, 17 meters per second. However, that's not x or y. I would actually like to solve for what its velocity initial in the x direction would be. And I'd also like to solve for what its velocity initial in the y direction would be, because there's kind of a component to it. And so if I were to kind of break this up into a triangle and put 17 on the hypotenuse, this is your velocity initial in x, this is your velocity initial in y. Now, I should point out, velocity initial in x, it's always going to be going the same direction in x, right? In the x direction, there's no external forces acting. The y velocity is going to change, though. It's going to start at 17, go to 16, 15, 14. Eventually, at the vertex, at the peak, its y velocity will be 0, and then it'll start coming back down again. So, anyways, long story short, we need to do a quick review of our trig lesson. This we did a few lessons back on vectors. And the way this is going to work is velocity initial will be 17 times the cosine of 60, whereas this one will be 17 times the sine of 60. Now we need to do a quick recap. I'm not going to show you all the little bits here, but the reason for it is that the adjacent is VIX, and so adjacent involves cosine, and the opposite is VIY, so that involves sine. Now, if you need a quick tutorial as to how I got there a little bit quicker, because I'm not showing every single little algebra step along the way, but if you need me to show you, pause the video, let me show you. But now I know what VIX and VIY are. Now, in theory, I could find these numbers and save them in my calculator, but another trick I want to show you is I'm just going to leave them as this from now on. So I actually know VIX and VIY. So that's actually all I was given, though. I was given a speed of 17 meters per second, and I was given the angle. Now, we've already solved part A, though. It asks for the vertical and horizontal components of the velocity. We have those, so we're done that. Part B then wants to know the maximum height the ball will reach. Well, maximum height means it's really asking me for dy. So if I were to write out some more variables here, let's keep going. dy is what we're looking for. But at this point here, I know a few things. I know the acceleration in the y direction is going to be negative 9.81 meters per second squared. And the reason why it has to be negative is that it was traveling up. These are positive velocities, but gravity's pulling it back down. So I do need to make the negative apply. Now, I don't know time, so that's kind of unfortunate, but I do know one more thing. I know velocity final in the y direction will be 0. And the reason why is that at the apex, at the vertex, the peak, at the peak of this parabola right here, I know that in the y direction it comes to a momentary stop. So it looks like I have 3 variables. I have a VIY, I have an AY, and I have a VFY, which means I should have enough to solve for my remaining 2. So let me look at the question again. Question B said the maximum height of the ball. So let's solve for D. So in order to make this work, it looks like I should use, let's see what formula. We need a D, I think we need this one, VF squared equals VI squared plus 2AD. That's the formula that involves all these variables. And we need to do some rearranging. So a couple thoughts here. VF squared really doesn't apply because it's 0. So I can make it negative VI squared, and then I can divide by 2a, and that will equal my distance. So now I like rearranging formulas before plugging numbers in. I think it's the better way to go. You don't have to do that if you don't want. You can plug numbers in here. But let's try this. I'm going to do negative, and then the VI in the y direction was 17 sine 60. And then it'll all get divided by 2, and then acceleration is negative 9.81. And one of the cool things you should notice here is the negative should really cancel, right? Which is good, because we expect a positive distance. So I'm going to try this now. 17 times sine 60, and I'm going to square that. Then I'm going to divide by 2 times 9.81. And I'm going to get a distance. Oh, I need to make sure I use proper brackets. I just did my calculator, and I got 0.649, and I realized that can't be right. And I think the reason why is that I didn't use proper brackets. So I'm going to try that one more time. I'm going to put all of 17 sine 60 in brackets. There we go. Okay. When I did it in my calculator, this bracket sign right here and right here, I didn't actually use those brackets there. So I calculated this. I got 11.04 meters, which makes sense. The guy's punting the ball pretty high up in the air, 11 meters in the air. That might even be a little bit too high. Maybe my numbers are not quite to scale. Maybe 17 meters per second is a bit too fast, but that seems in the ballpark. So because I may use this number again, I'm going to store this as A, just as I always do. So let's store this as letter A. And now we know the distance it traveled. And with sig digs, we get 2 sig digs, but we now have the maximum height the ball traveled. Now it wants to know the length of the time that the ball is going to be in the air for. And there's a couple ways we could do this. Because this is symmetrical, I could find the time that the ball is in the air for at the halfway point, and then times by 2. Right? Because if it gets kicked from the ground and leaves from the ground, it's going to be twice that, right? So I could just find that and then times by, this is me timesing the time value by 2. So why don't I do that? Why don't I utilize the information I have? And it's the same information as before. I'm going to use this formula here. D equals VFT minus 1/2 AT squared. I'm going to solve for time. Now, there are many other ways of doing this, by the way, right? Like I have all my variables. I just like this method here because velocity final was nothing. And so if I want to solve for time, I need to do negative 2D divided by A square rooted. That'll give me my time value. Now, keep in mind, this is going to be the time value at the halfway point. At the halfway point. And so using this formula here, I now solve for D. So D is actually 11.04, which I've saved, right? And my acceleration is still negative 9.81. So now I've solved for my time value. So I'm going to square root negative 2 times by 11.04, which I've saved as A. I'm going to divide by negative 9.81. And I got a time value of 1.50 seconds, which I'm then going to double and basically make it 3.0 seconds for the ball to travel all the way there. Right? So halfway up, halfway down. And we assume this is symmetrical. I mean, okay, putting spin on the ball or wind currents, that might screw things up. But yeah, we do have the length of time the ball's in the air for. Now again, I'm going to save that number. So I'm going to store this as letter B, because the reason why I want to store this as B is that for my final example, it asked me for what distance was the ball in the air for the x direction, right? Go back up to the top problem here. The horizontal distance the ball is going to travel, that wants to know how far it is here. Well, to know that, we need to know the velocity it traveled and the time it traveled for, but we have those. I know the initial velocity in x. I haven't used it since step 1, but 17 cos 60 is how fast it was traveling in the x direction, and that hasn't changed. Right? It's always traveling that direction. So to find dx, I mean really the formula was Vx equals dx over t. So if I take Vx and multiply by time, it should look like this. My Vx again was 17 cos 60. And my time value we just solved for was 3 seconds. So I'm going to take letter B and I'm going to times by 17 cos 60 to get a distance traveled in the x direction of, what do we get, 2 sig digs? Let's call it 26 meters. And there we go, we're done. So again, this is what I love about doing. Okay, so here's another example. What we're going to do now is we're going to throw a rock off the edge of a cliff. And so this is going to be kind of similar to the punting problem we just finished, but it's slightly different. Rather than the punter punting the ball up and back down with kind of like a nice distinct halfway point, because you're throwing the rock off the cliff, it's not perfectly symmetrical, which means that if you ever solve for the time at the halfway point, it's not quite even, because we can't account for, like, say, this missing distance that I'm drawing right there. And that kind of makes a bit of an issue. So we're going to solve similarly, but again, this is what makes physics so cool, is that it's not ever quite the same as each other. There's a bit of a different twist this time around. So let's draw out the scenario here again. What we're going to do is we're going to have, same as the punter problem, we're going to throw a rock off the cliff with an initial vector, and if I were to break it up here, it says it was 20 degrees, and it was 8 meters per second. But that means that I could break it up into, so the velocity initial was 8 meters per second, but I could break it up into the velocity initial in x as 8 cos 20, and the velocity initial in y as 8 sine 20. And so we could break this up into the initial amount in the y direction and the initial amount in the x direction. Keeping in mind the x direction is never going to change. It really isn't an initial in x, it is the velocity in x total. Right? So we do know that information. It's just the exact same as the punting problem. But I also gave you one more piece of info. We know that we are 15 meters above the bottom of the cliff. So it's kind of like the buffaloes being run off of head smashed and buffalo jump example as well. It's kind of similar there. So let's do a couple of things. So we need to know how long it's going to take the rock to fall. Well, we actually have enough information to solve this. How long it's going to take the rock to fall means we need to know the time value. Now, time is the one thing that is independent of all these values, but I do know some more things. For example, I could write out that I know that the distance in the y direction it will ultimately travel will be 15 meters. And I'm going to say negative 15 meters, because I know that it's ultimately going to travel down negative 15 meters. I also know the acceleration in the y direction will be negative 9.81 meters per second squared, which means that I actually have enough y dimensions. I have 1, 2, 3, 4 numbers. And so because I have all of those, I actually have enough to solve. I need the formula that involves a VI, D, A, and T, which is this formula here. Where is it again? D equals VIT plus 1/2 AT squared. And that formula would solve me for time. Now, one of the downsides to using this formula is that if you've recognized this scenario before, solving for time means that you need to use the quadratic formula, which kind of stinks because maybe you're not comfortable, you're not familiar using the quadratic formula. So I'm actually going to use the other process this time. We could use that formula and solve for t, but don't forget we can also use the formula and solve for the remaining variable. And so we could solve for the velocity final in y first. Why don't we do that? Why don't I use the formula VF squared equals VI squared plus 2AD. We'll use this formula and we'll solve for VF. So VF will be the square root of velocity initial squared, which will be 8 sine 20 all squared plus 2 times negative 9.81 and negative 15. I could tell you how fast this thing's going to be hitting the ground in the y direction, which I don't really need that number, but this is a nice end around for having to use the quadratic formula. So 8 sine 20 squared, do that in brackets, plus 2 times negative 9.81 times negative 15, and then square root the whole thing. I have now calculated my velocity final of y to be 17.37 meters per second. And I'm going to store that as letter A. Now, I don't really need that number, but it's a nice way to get out of the quadratic formula, because now when I'm solving for time, I can use really any formula. I'm going to use this one. D equals VF
plus vi all over 2 times time. And so to solve for time, it's going to be 2 times d over vf plus vi. So my distance traveled is going to be negative 15. My velocity final is a, oh, now I got to point something out here. You know when you square root a number? There's always a positive and a negative to the square root. This is actually a negative. And the reason why it's negative is that when it hits the ground, it's going to be going in the downwards direction. You always got to be careful of that whenever you use a square root, is that a square root could give you the positive, or it could give you the negative of a square root number. So my velocity final is actually negative 17.37. I got to be careful of that. Whereas my velocity initial was the 8 sine 20 number. And so hopefully I've explained this well enough here, but this number here needs to be negative, whereas that one's positive. So let's try all this now. I'm going to go 2 times negative 15, and I'm going to divide it by the negative a value I stored, and I'm going to add to that 8 sine 20. And I got a final time value of 2.0497 seconds, which I may as well store as b, because I'm fairly certain we're going to be using that again in the future. Now, in theory, you know how we could have used the quadratic formula? Let me rewrite it out again over off to the side here. We could have used d equals vit plus 1/2 at squared. And we could have used the quadratic formula to solve, but I bet you if we did it properly, we should get the same time value here. Now, I can check this one more way. Let's say I didn't use that formula. I could have even used the formula A equals Vf minus Vi over t. I could have solved for time that way. I'm just going to check my work. I don't really want to use the quadratic formula method, but just to check my work, it means that time is going to be equal to my two velocities subtracted each other divided by the acceleration. So again, velocity final was going to be negative 17.37. My velocity initial was 8 sine 20, and my a value is negative 9.81. Let's just double check and make sure I still get 2 seconds. So negative my a value minus 8 sine 20, and then take all that and divide by negative 9.81. And yeah, I still got the same number, 2.04 numbers. So anyways, that's one of the cool things about physics, more than one way of solving things. I could have used this formula. I could have used the quadratic formula. I could even have used this formula here. Really, same thing, more than one way. So let's go back to my checklist. What am I solved for? I wanted to know how long it took the rock to fall. I have that. Now I want to know how far from the base of the cliff it's going to hit. And we've come across this a few different times now, haven't we? Because that's now the x direction. In the x direction, your velocity in the x direction will be your distance in x divided by time. And so if I want to know dx, I'm going to take my velocity initial in x, which it never changed, in times by time. Velocity initial in x was 8 cos 20. And the time value I just solved for, it was 2.04, etc., which I've saved as b. So if I take that number and times by 8 cos 20, I have a distance in the x direction with, let's check sig digs. What do I need for sig digs? That looks like 2 sig digs. This number here limits me to 2. Looks like 15 meters. 15 meters. But it's actually a 15.409 meters. So I'm just going to store this as letter C, just in case I need it. I'm not sure that I will, but it's never a bad idea. So again, hopefully you've been able to follow along, but we've now solved all of these parts here. We know the time it's going to take. We know how far from the base it's going to land. Right? What we want to know now is the velocity of the rock as it hits the ground. And to do that, I need to redraw this picture. So I'm kind of hopping around a bit, but let's redraw the picture. We threw something off a cliff. It went up in the air, and it landed. And as it landed, you know how we made a velocity vector to begin with, where we figured out both the y and x components? Well, we need to do that as it lands. And so as it lands, we need to know its x and y components. And we can actually use Pythagoras' theorem to solve for like the resultant. And the good news is we know the x and y components. because the x component was, well, it's always traveling the same velocity. It's always traveling in the x direction. Where is that number? 8 cosine 20. Whatever 8 cosine 20 is how fast it's always traveling in the x direction. But in the y direction, it was traveling down. And I believe that number, we calculated out somewhere, it was 17.37 meters per second. But we saved that as letter A. So I actually have enough information here to use my letter A stored in my calculator and solve for the Pythagoras here using c squared equals a squared plus b squared. So I don't want to know just the y component or just the x component. I want the hypotenuse, and it's going to be the square root of 8 cosine 20 squared plus whatever letter A was squared, all square rooted. That will give me my resultant hypotenuse. And A, keep in mind, was about 17 meters per second. So let's try this. 8 cosine 20 all squared plus letter A all squared, square rooted, gives me on the resultant a velocity hitting the ground with 2 sig digs of 19 meters per second. It was actually 18.9, but it rounds to 2 sig digs with my angle. And so now I know how much speed it was hitting on the hypotenuse there. And so I did this one to make a point, even though I could have used Pythagoras' theorem, or the quadratic formula, using this formula right here, I solved for the velocity final in y just because I knew it might be useful to have in the future. And so even though the quadratic formula is a method of solving, you don't ever actually have to use it. You can always just solve for the remaining variable. So there we go. We've now solved all 3 parts. Like normal, if you have questions, call me over and ask for help. Otherwise, I'm going to move on to what I believe is our last example. Yeah, our last example. Here it is. It says a paintball is shot at an angle of 18.2. Okay, well, we've worked with angles before, right? And it hits a target 0.51 meters above the launch point after being in the air for 3.2 seconds. So if we could kind of imagine this scenario here. Here's a guy shooting a paintball gun. Let's say it's a one-handed gun, apparently. And he shoots this thing right here. And it doesn't actually travel in a straight line, though, right? We know that. The straight line's not true. It actually is going to travel in a little bit of a parabola, right? And in doing so, it's been in the air for 3.2 seconds, so I know my time value is 3.2. And it hits a target 0.51 meters above the launch point. So if the bullet could have gone straight, it actually hit the target a little above where straight would be, 0.51 meters above, which means I actually know the distance traveled in the y direction is 0.51 meters. It had a little bit of height gain to it. Now, we were given the angle, but I don't really know where to use the angle yet because we weren't given the velocity to begin with. We don't have that yet. But I do know more information, though. I do know that my acceleration in y is going to be negative 9.81 meters per second squared, which means as I look at what I have written here, I actually have 3 variables. Now, I can only solve in the y direction. However, in the y direction, that's not that bad. I can take that. Why don't I solve? Well, I mean, what's left in the y direction? I can either solve for the velocity initial in the y direction or velocity final in the y direction. I can solve for either of those, right? Now, the correct answer is let's solve for velocity initial in the y direction. And the reason why that's useful is that if I were to give kind of this initial triangle right here, remember how there's supposed to be a x and y component, and we know the angle in here is 18.2 degrees. Well, why don't we use the initial amounts? Because the final amounts we don't have any angles for. So why don't I solve for velocity initial y? Which means I have to use this formula here. D equals VIT plus 1/2 AT squared. And I have to solve for VI. So that's going to be D subtract 1/2 AT squared, divide by T, that'll be VI. So that's my algebra. Again, I can speed through this because of the asynchronous lesson, but if you've lost me as to how the algebra worked there, let me know. So let's plug in some numbers. The distance it traveled was 0.51 meters. Acceleration is negative 9.81. And the reason why I need to use the negative is that distance was up, but gravity's down. Time was 3.2 seconds. And then I have to divide by 3.2. This will give me a velocity initial in the y direction. So 0.51 subtract a half times negative 9.81 times 3.2 squared, and then divide by an extra 3.2. I have a velocity initial in y of 15.85, etc. meters per second. It's positive, which makes sense. That's a good sign. And I'm going to store this as letter A, as I feel like I'll be using that again. Well, here's what that means we've solved for now. We now know the y component. Now, if we know the y component and we know the angle, we can actually solve for the x component. We could solve for the x component. So if I were to kind of draw a bit of a triangle going on here, this is of the initial shot. I now know that the y component was 15.85 meters per second y component. And I know the angle in the corner there was, what was it again? It was 18.2 degrees. I should be able to solve for the x component. Now, this is not one of the standard calculations, but using trigonometry, this is an opposite and this is an adjacent. This is tan. So if I tell you that the tan of your angle is equal to your opposite over your adjacent, and we're trying to solve for the adjacent, you could say that the adjacent is equal to your opposite over tan theta, which means that your opposite was what we just solved for, 15.85, and tan theta would be the tan of 18.2. If I do this, I should be able to calculate what the adjacent side is. And the adjacent side is your x velocity. So I'm going to take that 15.85 number, and I'm going to divide it by tan of 18.2. And I've calculated that the adjacent side, which I believe is the velocity in x initial, is actually 48.22, etc. And I may as well store that as letter B. So here's a quick recap of what we've done. Go back up to the top. We used the y dimension data to calculate the initial velocity in y, which is really, if I were to use a new color here, just because this is vectors again, we now know the y initial velocity. But the y initial velocity is not really that useful. What I really need is the x initial velocity, which I just solved for using trigonometry. And so I now know that my velocity initial in x was 48.22, etc. meters per second. And it's always traveling that speed. But hang on. If I know that the time is 3.2 seconds, haven't we been here before? Can't we solve a distance using that? So to go back down to the very bottom here and finish this off. In the x direction, distance, well, let's do it the long way. Velocity over time. No, that's not right. Try again here. Velocity is distance over time. But if I rearrange to get distance, distance is velocity times by time. We know the velocity is 48.22 meters per second. And we know the time, I believe, was 3.2 seconds. So if I take letter B in my calculator, and I times it by 3.2, I have a distance of 154 meters. So that means that it must have only gone up a height of a half a meter, but it traveled a total raw distance of 154 meters. However, that's not actually right. And the reason why is that these two numbers only have 2 sig digs. So it should be 1.5 E2 meters. That's how far it's traveled. It could have actually been 153 or 151 meters. I don't know. It has to be rounded to the nearest tens. I can't have a precision to the nearest 1 meter. The best I can give you is a precision to the nearest tens of a meters. So I went to 150 meters basically when you round it. So, okay, again, the whole beauty of doing this asynchronously now is that if you understood kind of that version of it, that's great. And if not, I'm just checking my work over. If not, if that didn't make sense, you should ask me for help. So that's it for my video. One thing you may have noticed, by the way, is that this is going to be the splice of a few different videos. I had to start and stop a few of these examples. So if you have any questions, let me know. Otherwise, that's it for our lesson. Thanks, everybody.